Welcome back again to the video series. Today we'll be doing independent measures t-test. We will find that this is very similar to one group t-test, but again, because we don't have one group, we're going to have two groups that are completely independent of each other. That adds a little bit of complexity, but it's not bad. In this case, we actually have, for example, a control group and an experimental group instead of one group compared to some population mean. So if we review what we've done before, it's exactly the same logic. We're going to have an actual mean that we subtract from in this case, a population mean. So we'll have two means that we subtract, that we've actually observed this. And then we'll have the estimate based on the sampling distribution. Here it is the standard error, and that comes from the standard deviation. We've estimated the standard deviation based on our sample, and again, that comes through the sum of squares. So if you've spent some time on the previous videos, you should be fairly comfortable with that. The equation in the second column over on the other side, you'll note that it's very much the same thing. In the numerator, I'm subtracting two means. In this case, instead of a sample and a population, for the independent measures t-test, I have two samples. In the denominator, I also have the estimated sampling distribution, but instead of standard error, it's now called the standard error of the difference of the mean. Really, all that I am doing is, since in this case, with the one group t-test, I am estimating the sampling distribution based on that one sample. I'm using the sample to estimate the sampling distribution. All I'm doing in the independent measures t-test is I'm using both samples to estimate that sampling distribution. So I'm using both of those to create a better estimate. The more observations I have in my estimate, the better that it's going to be. I still am going to be computing. In this case, you'll see that that value, the standard error of the difference, can be computed by the standard deviations, just like before. Well, actually, in this case, it's the variance because I'm squaring them. And so that can be the same thing. But there's actually an easier way to do that. There's a couple things, however, that I want to take a moment to point out. First of all, this is the notation for standard error of the difference of the means. This is not a computation. I have had students make this mistake, so I want to point this out very carefully. Notice that x bar 1 and x bar 2 are both in subscript. This is not a regular case x bar 2. So what this is not reading, do not do this. Some students have read this as take the standard error for group 1 and subtract the mean from group 2. This is not a subtraction. This is not a computation that you're doing. It's just a notation. So this all fits together in one thing. It's a notation. Don't do any computation in this part of it. Standard error, this is the notation, equals, this is your computation. So just as before I took the standard deviation divided by the square root of n, over here it's asking you to take the variance for group 1 and group 2 and then take the square root to get the standard error of the difference. It's conceptually exactly the same thing, but I don't like this formula, and a lot of textbooks have this formula because it asks you to calculate all the way to the variance and then kind of back it back out to get the standard error of the difference. There's a simpler way to do it. I don't have to go all the way to the variance and then get there. This formula here is algebraically equivalent. So in this case, all I have to do is sum of squares. Remember, to get to the variance, I have to do sum of squares, divide by n minus 1, that gives me the variance, then I go here. But here I don't need to go to the variance. I can just end at sum of squares, divide by number of observations for group 1 times the quantity, number of observations for group 2 minus 1. That is algebraically equivalent of this one. So even though some texts have this formula and it will work fine, I don't like it. I like this one. It's easier. It's much closer matched to what we've done in the past. There's a caveat though. This formula only works if both of your groups are of equal size, meaning the number of observations in group 1 is the same as the number of observations in group 2. But we can use effectively this formula, change it a little bit, and it will always work. So note that I still have sum of squares for group 1 and sum of squares for group 2 in this formula. I've just made some slight changes to how the ends are arranged, and now it works fine every time. And so this one will always get you there to the standard error of the difference, but the numerator is the same, divided by the standard error of the difference. The degrees of freedom for an independent measures t-test is the number of observations for group 1 plus the number of observations for group 2 minus 2. Why is that? Because we have two groups now, and we're using those two samples to estimate two population parameters, so we lose 1 degree of freedom for each estimate that we're doing. So here's the computation, but it is based on everything that you've done before. You're calculating an average. We've done that many times. You're calculating a sum of squares. We've done that many times. We're just going to do it for group 1. We're going to do it for group 2. And then we're going to plug everything into this formula down here that you see. So what does significant mean again? If you remember this, I have a population. So this initial distribution is some overall population from which I am taking a sample. I then apply a treatment to that sample. If the treatment works, then that means it is no longer the original people, but it is now the sample plus the treatment. I say this in a different video, but I'm going to repeat it again here. Imagine the silly example of if I have somebody that's a brunette and I apply a treatment, I'm changing their hair color and it works. They are no longer a brunette, they are now a blonde. So they are no longer in the brunette population. It is now sample plus treatment. They now belong in the population of blondes because it is the sample plus the treatment at that point, so it becomes something else. That's what it means for a treatment to work in a statistically significant way. It's a mathematically observable way. So again, I'm actually looking at that difference between the actual groups. So this is my control group, but then I've taken a sample from there. So the control group, I haven't added the treatment. The experimental group, I've then taken and added the treatment to. So effectively, I will have one sample that is still in the original population, brunettes, if you will, and then I'm going to have the other one, which is in the now they are in the blonde population if it worked. So basically, one would be the control group, the other would be the plus treatment. If that distance between groups is more than would be expected when we average the shape of those two distributions, because effectively that's what this denominator is doing. I need to estimate the variance of that sampling distribution. Remember, standard error, conceptually the average distance of a mean from the mean of the means. With one group t-test, we were estimating that with our one sample. Now we have two samples. So let's take the, conceptually speaking, the shape of those two samples and use both of those to estimate the shape of our sampling distribution. So in this case, if I was to conceptually take the shapes of those two distributions and average them together, that would be the dotted line. So now, using both of those samples to estimate my sampling distribution, so how far do I expect that mean to be, we can compare the actual observed difference with the expected difference. If the observed difference is more than we would expect randomly by chance, then that means that the treatment actually works. So again, that's that actual difference. The observed difference, as we see here, if it's big enough, it'll be in the tails. That would be indicative that it's more than we expect by chance. So how do we compute this? Well, what I'm going to do is revisit the early experiment that we had with birds that were digging up the worms, the mealworms, and the nuts. If you didn't watch the original videos, then basically what this comes down to is birds prefer the mealworms. They we give them a bunch of food, they bury the worms and they bury the nuts, they're going to hide it, and then they're going to dig it up later. We want to know two things. Do they remember where they buried it? Do they remember when they buried it? And I guess the third thing really is, do they know that the worms rot and become unpalatable? If they know all of these things, then that means that early on, they should dig up more worms than nuts because they prefer those. They're going to want to eat those first because they know that they rot. Whereas after 124 hours later on, if they know that they rot and they know that where they buried them, they're not going to spend any time digging them up because even though they prefer worms, after that much time they will be unpalatable and they won't dig them up. So before, when we did this example, we actually did 2 one-group t-tests. But it makes much more sense to do this in one experiment. So I will have group 1, which was the 4-hour group, and then group 2 will be the 124-hour group. If they did understand that there was a difference, then I should see a difference between the number of mealworms that this group digs. This group should dig significantly higher percentage of worms than the 124-hour group. This group should dig significantly fewer worms after 124 hours. So what do I need to do? I need to do computations very much like I did before. My formula is calling for the average of group 1. I need to add these together and get the average so that I can then compute the sum of squares for group 1. So once I have the average, that will go in all of these blanks here. So I'll subtract 81 minus the average. Then once I have that value, I need to square it. So then once I have the squared values, I add them together, and that's going to be my sum of squares for group 1. Likewise, I do the same thing for group 2, compute the average, fill in the blanks next to the values, subtract it, square it. That's going to give me my squared deviations. Then I sum those together and I'll get my sum of squares. So then once I have those values, I can go to my toolbox, fill in my toolbox over here. Again, my degrees of freedom is going to be N1 plus N2 minus 2. That will give me my degrees of freedom to fill in my toolbox. So I'm going to get out of the way here. I encourage you to pause the video, work this through, see if you've practiced enough to be able to do this on your own. Welcome back. If you have computed this through, then we also need to come up with the hypotheses. Remember, to get the hypothesis in statistical notation, you go to your numerator from your t formula. So my null hypothesis says that there will be no difference between the number of worms that this group ate and the number of worms that this group ate. So basically, x bar 1 equal x bar 2. What is x bar 1? It's the average percentage of worms for my 4-hour group will equal the average percentage of worms for the 124-hour group. If it did work, then those will not be equal. It will be x bar 1 does not equal x bar 2. Same wording, but now it will be not equal to. If you computed this through, then what happens is you now have your hypotheses. These are all of the values that you should have gotten. So my degrees of freedom here should be 22. T of 22 equals 9.57. But once I have a t observed, I need a t critical value. I've given you a part of the t table so that you can look this up. Again, I have an alpha of 0.05 two-tailed test, and I have a t-crit of 22. So when I put those two together, that's going to give me a critical value of plus and minus 2.074. So 9.57 is going to fall all the way over here in the tail above positive 2.074. That indicates that it is sufficient to reject the null hypothesis. So the birds do appear to remember the food type and time. And since group 1 has the higher average, 76%, then this analysis does support the supposition that birds know what was buried, where it was buried, and when it decays or that it decays, because by the time we get to the second group, they only dug up 20% of worms. That means that basically, even though they prefer worms to nuts, after 124 hours, they know that the worms are nasty, so now the preferred food is nuts, and they spend their time digging up nuts instead of worms. We have made it through the independent measures t-test, so we're now comparing two groups that are independent from each other. But again, I hope that I have showed that these computations are very much the same as before, but more importantly, conceptually, we are doing exactly the same thing. The numerator is always the observed difference between groups. The denominator is the expected or estimated difference based on the within group observation or the within group distribution that we have. Again, I hope that the video series is helping you with your enjoyment of statistics.